All right, new topic. So the integral from 1 to infinity of 3 times 1 over x squared dx, well, that's going to be 3 times the integral from 1 to infinity of 1 over x squared. So I can just pull out a 3. What I'm getting at is the following idea. Think of this as a function, 3 times 1 over x squared. Maybe that's your function f. Think of this as a function g, 1 over x squared. This function is 3 times as big as this function. Because this function is 3 times as big as this function, this area here is 3 times as big as this area over here. So I'm getting at the following idea. Suppose g of x is 3 times as big as f of x. Then the area under the curve of g of x is 3 times as big as the area under the curve of f of x. So it's like this is my g, this is my f. If g is 3 times as big, if g here is 3 times as big as f, then the area under the curve of g is 3 times the area under the curve of f. Okay. So, all right, let's say I got two functions g. So two functions. F of x equals 3x squared, g of x equals x squared. Let's say I do f of x divided by g of x. So in other words, I do 3x squared divided by x squared. That gives me 3. What this is telling me is f of x is 3 times as big as g of x. That's what that tells me. So, new functions. F of x equals 3x squared plus 1. G of x is x squared plus 1. What I'm going to do is I'm going to look at the limit as x goes to infinity of f of x divided by g of x. In other words, I'm going to look at the limit as x goes to infinity of 3x squared plus 1 all over x squared plus 1. Well, you can crunch find this limit, crunch those numbers. The limit is 3. Let's think about what this is telling us now. So we're saying as x goes to infinity, f of x over g of x goes to 3. So we're saying when x is really, really big, f of x divided by g of x is really, really close to 3. So what we're really saying is when x is really big, f of x is about 3 times as big as g of x. That's what we're really saying there. New example. F of x equals 3 over root x plus 7. G of x equals 1 over root x. Let's do the limit as x goes to infinity of f of x divided by g of x. That's the limit as x goes to infinity of 3 over root x plus 7 all over 1 over root x. So compute that limit. That limit is going to be 3. So again, think about what that tells you. When x is really big, f of x divided by g of x is close to 3. So, when x is really big, f of x is about 3 times as big as g of x. Okay, let's look at this integral now. the integral from 5 to infinity of 1 over root x. So I'm integrating g. So that's the integral from 5 to infinity of 1 over x to the 1/2. We know this, this integral is infinite. So 1 over x to the p is less than or equal to 1. Infinite amount of area. Okay, so the area under the curve of g of x is infinite. When x is really big, f of x, which equals 3 over root x plus 7, is about 3 times as big as g of x. Well, but then, when x is really big, the area under the curve of f of x. So past some point. So we're only considering the area under the curve past some big number. So when x is really big, the area under the curve of f of x, so past some point, is about 3 times as big as the area under the curve of g of x. Well, here's the area under the curve of g of x. It's infinite. But that must mean then the area under the curve of f of x must then be infinite. Because eventually, past some point, the area under the curve of f of x is 3 times as big as big as the area under the curve of g of x. So in other words, the integral from 5 to infinity of 3 over root x plus 7. Using this reasoning, we can say, okay, this area under the curve is infinite. Why? Well, for this other function back here, the area under the curve, we know it's infinite. And we're saying past some point, so when x is really big, this function is about 3 times as big as this function. So past some point, so way off in the distance, if you take the area under the curve past that point, the area under the curve here will be about 3 times as big as the area under the curve over here. So past some point way off in the distance. Okay, but then past some point, this guy will have more area under the curve than this guy. So past some point, so way off in the distance, way past when x is 5, the area under the curve here will be about 3 times as big as this area, way off in the distance. So if this area is infinite, this area must be infinite. Okay, let's look at another example. F of x equals 5 over x squared plus 17. G of x equals 1 over x squared. Let's find the limit as x goes to infinity of f of x divided by g of x. In other words, we're finding the limit as x goes to infinity of 5 over x squared plus 17 all over 1 over x squared. That limit is 5. So what that is telling us is when x is really big, f of x is about 3 times as big as, or is about 5 times as big as g of x. So let's look at the integral from 3 to infinity of 1 over x squared dx. So I'm integrating g. We know that this area is finite. In fact, actually, I take it back. Let's switch to 1. Let's integrate from 1 to infinity. So not only is this integral finite, we actually computed this integral earlier. The integral from 1 to infinity of 1 over x squared, it's actually 1. Anyway, so it's finite. Okay, now, when x is really big, we said that f of x is about 5 times as big as g of x. So when x is really big, the area under the curve of f of x is about 5 times as big as the area under the curve of g of x. Okay. Well, so let's say I want to look at the integral from 1 to infinity of 5 over x squared plus 17. I don't know what this integral is. I mean, we could actually compute the number by hand, but it doesn't matter. I do know that this area now has to be finite. The reason is, past some point, so way off in the distance, way past 1, this function here is about 5 times as big as this function. So past some point, the area under the curve of this function is about 5 times the area under the curve of this function. So way off in the distance. So maybe 1 over x squared looks like this. And so we don't care about 1 right now. We're looking way off in the distance. So way out, I don't know, way out here. What we're saying is if this is 1 over x squared, whoops, I'm sorry. If this is 1 over x squared, 5 over x squared plus 17, well, it's about 5 times as big. So way off in the distance here, the area under the curve for this function, 5 over x squared plus 17, off in the distance here, this area under the curve is going to be about 5 times as big. Well, this area is finite. And so, sorry, that's supposed to be keep going down. So if this area under the curve is finite, this area under the curve must be finite. It's bigger. It's about 5 times as big. So this area under the curve, the bigger, so this little area under the curve, we know it's a finite number because 1 over x squared, the integral of it, is finite. So the area under the curve, we know this area under the curve here, it's way less than 1. The area under the curve of the bigger function, 5 over x squared plus 17, this area, it's got to be about 5 times as big as this area. It's got to be a finite number then. So the integral from 1 to infinity of 5 over x squared plus 17, it must be finite. So this integral must be convergent. So this idea is the limit comparison test for integrals. So it says, if the positive functions f and g are continuous on the interval a to infinity, and if the limit as x goes to infinity of f of x over g of x is L, well, where L is between 0 and infinity, then the integral under the curve, or the area under the curve of f and the area under the curve of g must either both be finite or infinite. So, what this theorem is saying is if eventually f is L times as big as g, then eventually, past some point, the area under the curve for f will be about L times as big as the area under the curve for g. Well, then if the area under the curve for g is infinite, the area under the curve for f must be infinite, because past some point, it's L times as big. And if the area under the curve for f is finite, then the area under the curve for g must be finite, because the area under the curve for g, past some point, is L times as big. So L times a finite number is still a finite number.